Problem 29 of the spiral kinematics activity states, a car traveling at 16 meters per second sees a truck 20 meters ahead traveling at a constant speed of 12 meters per second. After thinking it over for zero point 0.8 seconds, the car starts to accelerate at 4 meters per second in an attempt to rear-end the truck. The truck driver has paid up insurance, so doesn't care. The car driver's motive is unknown. So here's the spreadsheet. The first thing that I always do is set up the column headers. And so, of course, we have a single column for time because the time is the same for both of the objects. And then we need position, velocity, and acceleration for the car, and then position, velocity, and acceleration for the truck. And so I've set that up. The next thing I typically do is to deal with the time, and you have to read the problem to decide what time step makes the most sense. And since we have something happening after 0.8 seconds, that I chose 0.1 seconds. And so I, of course, put in a 0, and then I put in a 0.1, and then I highlighted those two that contain the pattern. Then I went to the bottom right hand corner, dragged down, and I don't know ahead of time how far I have to drag, so I just dragged down a bit. The next thing that I did is go through to identify what the initial conditions were, and you would typically do, well, you should always do a motion diagram ahead of time where you decide where the origin is, what the positive direction is, and then decide what are the various signs associated with motion. And so in this case, they're both moving in the same direction, and so chose everything to be positive, chose the car to be at the origin, and it has a velocity of 16 meters per second, and there's no acceleration initially. The truck's 20 meters ahead traveling at 12 meters per second, and it doesn't accelerate during the entire period of time. Once I have this second row set up that has the initial conditions, then my next step is to deal with the accelerations, which in this class, when there's acceleration, it's constant. So I set up for the first 0.8 seconds the car having 0 acceleration, or an acceleration of 0 meters per second, and then I set up from there on for it to have 4 meters per second, and then the truck has 0 meters per second the entire trip. So with that, it's time to start entering equations. And I'm going to add a slight twist to this version so that this can serve as a template for whatever time steps that you're going to use in the future, and I guess is probably really more in keeping with the physics definitions. So I'll start here with the position of the car, and if I want to know the position of the car in the future, I know that that is equal to its position in the past plus the velocity that it is traveling at that time. But you'll remember the point is that if there is accelerated motion, that just clicking on this cell next to it won't get us as precise of a model, because if I have a changing velocity, it would be best to do an average. So I'm going to do an average here of the velocity at the beginning of the interval plus the velocity at the end of the interval divided by 2, and that gives me the average velocity. Now what I need to do is multiply that by the time step, and in the past what we've done is just put it in as a number, but if I think about the way we use this as a definition, that the we have velocity being the change in position over the change in time, which gives us this equation initially that I'm going to put in here the change in time. So the change in time would be the final time minus the initial time. So again, this says that my position in the future is equal to my position in the past plus my average velocity, and that's why we've got that averaging going on, times the time step, which is the final time minus the initial time. Now, don't pay any attention to what these numbers are yet, because it's basing this on values that aren't there yet. So, now what I'm going to do is set up the equation for the velocity of the car. And so, the velocity of the car in the future is equal to the velocity in the past plus the acceleration. And again, we don't have changing acceleration during an interval, because in this class we want to keep it as quadratic, not go up to involving jerk. So I'm going to click there, and then that's going to be times, and again in the past we usually just typed in the numeric value for the time step, but if we build this way, we can then use it as a template and go back and change the time step, and everything will be hunky-dory. So the time step is the final time minus the initial time, and we're then golden. We're going to say the same sort of thing here. So as far as the truck's position, that the position in the future is equal to the position in the past plus the average of the velocities during that interval times the time step. And then we do the same sort of thing for the velocity of the truck, because we know the velocity of the truck in the future is equal to its velocity in the past plus the acceleration times the time interval. And so that's good. So what I'm going to do is highlight these two cells that contain the equations for the position and velocity of the car and drag them down. And then I'm going to do the same sort of thing for the truck's position and velocity. And then I'm going to look to see if I can see where the car might have caught up with the truck. And so I can see at this point the car is right on the truck's bumper, and here the car is front bumper is in the back seat of the truck. So somewhere between here and here is where the collision took place. And so we have a solution here, and if I'm looking, that it's probably somewhere pretty much in between those two. The other thing that I would probably want to do is go back here and look for these values, because when we are doing the solutions, that we would have, okay, what are um, T1, R1, V1, A1, excuse me, T1, R1, V1 for the car, R1, V1 for the truck, and then we would look at the accelerations in between. So since these are given, that's fine. But then at this point in time, this would indicate the twos, the R2, V2, and A12 for both the car and the truck. And so as we solve this by hand, then we could go ahead and compare these numbers. And then we would, when we're solving for the threes, which is to say the T3, R3, V3, and A23s for both the car and the truck, we could use these numbers as a comparison. Now, if I have this kind of spreadsheet set up already, I would be able to plug in the time steps, the initial conditions, and any of the variations of accelerations very, very quickly. And it would take me less than a minute probably to actually solve for the numerical answers. One of the reasons that I show you this is that this will take you way less time than using the algebra. Now, the algebra is important because it's part of the curriculum and you should know where stuff comes from. But again, in the real world, frequently solutions are derived from numerical solutions rather than equation-based. And this is equation-based, but it's not doing all the fancy algebra. So I hope this reinforces for you that computational physics is an important branch of physics, and as you move forward in your career, educationally and beyond, the likelihood that you'll have to do all of the algebra that's associated with a problem like this is not something people would pay you to do or necessarily expect you to do unless you're a physics major. And they shouldn't even then, but that's a whole separate issue. So, here's the answers. I hope you enjoyed this screencast, and you're about to see a video. And I did it not as a screencast, excuse me, as a pencast, because I did it on the whiteboard and then videoed an explanation because that's what made sense to me to do at the time, and it would take me less time. But you'll see that the solution algebraically is fun if you like mathematics, but it's involved. So, enjoy.